Okay, good afternoon. It's 3 o'clock in Europe, and we are starting our afternoon session of today.
Hello.
Hello, Jose.
Hello. Hi, Professor Gregory.
Hello. Yes.
How are you?
Great to see you. Everything fine. Can you share your screen?
Yes. Wait a moment, and my camera it's not working.
Yes.
I'll be back.
Okay. Okay, so we'll be we'll have only one speaker this afternoon, Jose Rodriguez. And for today, that ends our session. Okay, Jose, we can see your presentation, but we cannot see you.
Yes, I have problems with my camera. I don't know.
Well, it's not a
Okay.
too serious. Okay, you can start.
So you see my screen, yes?
Yes, yes.
Okay. So, well,
okay,
good afternoon, everybody, and thanks for the invitation. And I'm going to talk about, give some remarks, general remarks on a semi-analytical method to analyze the evolution of ellipsoids via gravitational waves. So this is the work that I have done in a couple of years in collaboration with Professor Jorge Rueda. So first, I'm going to present a semi-analytical approach that can be used to analyze the post-merger object in double white dwarfs mergers or binary neutron stars, or in other scenarios. This semi-analytical approach is very useful since we can get insights and extract information using very simple calculations. So in this work, the dynamical evolution of the object is driven only by gravitational wave emission only. And as we will see, there is a degeneration between ellipsoids and binary system regarding only to the gravitational wave templates. Also, this method can be used to extract some information in the transition from a Jacobi ellipsoid, well, near to the Jacobi ellipsoid, into a Maclaurin spheroid that is seen, well, we argue that it's seen in long GRBs in the binary-driven hypernova scenario. So first, there is the seminal work of Chandrasekhar about Maclaurin spheroids and, in general, ellipsoidal figures of equilibrium. And these objects are rotating self-gravitating configurations that sustain equilibrium through the rotation, and also through internal motions, such as with vorticity. The first and the most simple objects are the Maclaurin spheroids that we can visualize like rotating pancakes. Yes, they are like pancakes. And the second ones are the Jacobi ellipsoids that we can see like a rotating American football ball. The first works were done assuming that the matter is incompressible. So this is equivalent to say that the polytropic index is equal to 0. So we will use for the variables normalized ones the spin, the angular momentum, and the total energy of the object. Here we can see the equilibrium sequences for the Jacobi and the Maclaurin ellipsoids. The Jacobi ellipsoid and the Maclaurin spheroid, sorry. And E is the eccentricity that is defined as 1 minus lambda 3 squared, the square of 1 minus lambda 3 squared. This is a cartoon of the ellipsoid. We can see the axis here, A1, A2, A3, and we assume that the ellipsoid is spinning along the one axis that we call A3. So this is the equilibrium, these are the equilibrium sequences, and we can see a bifurcation point here where the Maclaurin spheroids bifurcate into the Jacobi ellipsoids. This point marks an instability, a secular instability. There is another stability, but this is a dynamical stability of the Maclaurin spheroids that is given by the maximum in this plot of spin versus eccentricity. Here we can see the angular momentum, and also we can see the bifurcation point. Well, this is well in the 70s and in the late 60s, these objects were studied regarding to the gravitational wave emission. First, Chandrasekhar argued that these objects evolved from a Jacobi ellipsoid to a Maclaurin, given that the Maclaurin is axisymmetrical. So they evolved through along the Jacobi sequence. But this was wrong, as was later shown by Bonnie Miller, because the Jacobi sequence does not have a constant circulation. And from the dynamical equation, from the quadrupodal emission, you can show that the gravitational wave emission evolution is given by a constant circulation. So Chandrasekhar was wrong, and Bonnie Miller worked the correct evolution, but in this in the approximation of an incompressible object. So later in the 90s, Lei, Razio, and Shapiro made a step towards generalizing this work and introduced compressible models described by internal matter with a polytropic equation of state. And we can compute, calculate, and we can, let's say, analyze the evolution in a very simple manner through adiabatic sequence along equilibrium sequences, but not the Jacobi sequence, but the Riemann S-type ellipsoid. So what are Riemann S-type ellipsoid? Riemann S-type ellipsoids also have the shape of a rotating football ball, but they also have internal motions with vorticity. And the vorticity is in the same direction of the spin. So we call this type of ellipsoid Riemann S-type ellipsoids. And here we can see the evolution of the ellipsoid. So the evolution driven by gravitational waves is characterized by a constant circulation, and we can see, for example, in this plot, we have in the horizontal axis, we have the lambda 2 parameter, that is the radio of the A2 over A1. And when this radio is equal to 1, it means that the ellipsoid is symmetrical along is axisymmetrical. So we have we arrive at the Maclaurin spheroid. So the evolution begins, you can see, you can begin very near the Jacobi sequence, and you continue the evolution towards the Maclaurin spheroid. If the final point is after the secular instability, the Maclaurin ellipsoid can continue evolving towards the Deakin-like ellipsoid. So the Deakin ellipsoid are football balls as ellipsoids. The shape is also like a football ball, but they are not rotating. But the physical mechanism that causes the equilibrium is the internal motions of the object. So we have like two contrasting objects. The first is the Jacobi-like that is rotating but no internal motions, and the other one is the conjugate one that is the Dedekind ellipsoid that is not rotating but has internal motions. The internal motions are the responsibles of the equilibrium. So the upper part of the plot, the ellipsoids continue the evolution towards a Dedekind line. In the lower part, they end in a Maclaurin spheroid. Also, in the right part of the plot, we can see the Jacobi-like, and we call it Jacobi-like because they are a spin-off. So as they evolve, they lose angular momentum and energy, but let's say like counterintuitively, they spin up. On the other hand, the Dedekind line are a spin down sequence. Here we show the evolution for a compressible ellipsoid with polytropic index 1 and different values of the circulation. The circulation is constant along the sequence. So here we can see the comparison between a compressible and an incompressible model. So we can see here how the bifurcation and the location of the maximum changes as we introduce new physical effects like the polytropic index and the compressible matter. Next, I show you the evolution driven only by gravitational waves. I state that because I want to make clear that point. I am only considering a gravitational wave emission. So here we have the quasi-static evolution, like the Landau-Lifshitz evolution for a binary system that is a sequence of circular orbits. So we have here a sequence of Riemann ellipsoid type S objects, and here we can see the evolutions towards the final Maclaurin spheroid. And here I check if this approximation is correct, because I am assuming that the evolution is adiabatic, it's quasi-static. It means that the typical time of the rotation is less than the gravitational wave emission time scale. So here is the f dot, this is the gravitational wave, or you can only, there is a factor of 2 between the gravitational wave and the rotational frequency. So they are equivalent. So well, the important thing to to consider here is that this adiabatic parameter is always less than 1. So we are in a region that the approximation works. Now we solved the dynamical equations, taking into account all the dynamics of the ellipsoids and the gravitational wave emission. And we can see the actual evolution of the ellipsoids. It's shown by this wavy line, and the dashed lines are the equilibrium sequence that we have seen in the last slide. So we can see that the evolution, the actual evolution calculated by solving the dynamical equation is driven along the equilibrium sequence. So we have confirmed our hypothesis. And these are the evolutions of the ellipsoid. And here I put for comparison and contrast the evolution between the comparison between a compressible and an incompressible model. We can see that they are very different. The compressible ones reach a higher frequency. Next, we can, well, since we have the evolution, the exact evolution, we can compute the gravitational wave, yes, from the quadrupolar, from the Newtonian quadrupolar expression, and we can see that the gravitational wave is of the order of 10 to minus 22, the gravitational wave amplitude for an object located at 1 megaparsec. So the one conclusion that we can extract from this analysis is that the object is very short-lived, less than a second. So in less than a second, it reaches the Maclaurin spheroid configuration and stop emitting gravitational waves. So, well, from the astrophysical point of view, this object can be the result of the collapse of the carbon oxygen core in a binary driven hypernova driven scenario. So it's very important to check if the estimates are agree with the exact dynamical evolution. Also, this is very important because we can say that there is a new form of multi-messenger astronomy with regarding the binary driving hypernova scenario, because you can see first these short bursts of gravitational waves, and then you can see the gamma ray bursts emitted in this scenario. Also, from this method, you can calculate the energy emitted in gravitational wave during the transition to a Maclaurin spheroid, and as you can see, is of the order of 10 to 52 erg. And here I show the total energy emitted in gravitational waves as a function of the initial frequency. I leave this like a free parameter because we don't know all the details, the physics involved in this phenomena is very complicated. So I leave that free, but we can see that regarding the initial frequency of the Riemann ellipsoid, the emitted energy is of the order of 10 to the 52 erg. And also I put some different curves we representing different initial eccentricity. Next, well, this is regarding the rotating ellipsoids modeling neutron stars. So the polytopic index can be between 0.5 and 1. Now we can go to another astrophysical scenario where we can model new white dwarfs. So And in this scenario, the polytropic index is close to 3. The relativistic regime, the high relativistic regime. And it's important that here we can see there is a new phenomenon, there is an early period of increasing gravitational wave frequency and amplitude. Yes. So in this scenario, we see a chirping, only a chirping in the frequency, but not an increase in the gravitational wave amplitude. In this scenario, we see an increase in the amplitude in the initial part and also an increase in the frequency. So we have a chirp like a binary system. This is very important. This is very interesting because there is a degeneracy between a binary system and a chirping ellipsoid that we call a cell. Here I show you the time scale of the gravitational wave for these objects that correspond to a white dwarf with a model by a polytropic equation of state with n equal to 2.95 and a total mass of 1 solar mass. Now next, I show you the intrinsic gravitational phase time evolution of these cells and compare it to the parameter of a binary system. So the intrinsic phase time parameter is defined as the square of the angular frequency over the time derivative of the frequency. So this intrinsic phase evolution parameter is very important due to the fact that we can calculate from this parameter the change in the phase when the system changes its frequency. Because when we have two systems that are exact monochromatic, they are totally degenerate. We cannot make physics with a gravitational wave that is totally monochromatic. It can be anything. So these are like dead systems because you cannot say anything about it. Now, what we need is that the system changes its frequency and we can, in principle, extract some information. But as you can see here, the gravitational waves from a binary system and a ellipsoid, a chirping ellipsoid are degenerate because they change the frequency following a same power law. So they are totally degenerated in this first part of the evolution. Now, the degeneration is given by this relation between the mass of the chirping ellipsoid and the chirp mass of the binary system. So you can say that I have detected a binary system with a chirp mass of, let's say, 0.5 solar masses, but also you can argue that these correspond to another cell, to another object that is a rotating ellipsoid that is also chirping but has a different mass. In this plot, I show you the characteristic strain of these objects, and you can see that the characteristic strain is above the Lysa and Taijin noises, so they are detectable in principle. Now, here I compare the difference between the phase evolution of a chirping ellipsoid and a binary. Yes, so you can see that you can match them in a point and they continue to evolve quasi almost indetectable. They are the same for a long period of time, given that these objects are very slow. The evolution is very slow. They are quasi-monochromatic. And then the right plot shows the equivalence between the mass of the cell and the mass of the chirp, the chirp mass of the binary system. You can see the total degeneracy. So if you detect a quasi-monochromatic source, that is that you detect with Lisa after doing the match filtering analysis, you can detect the amplitude, the frequency, and the time derivative of the frequency. Once you have these parameters, you can extract the chirp mass, but also you can argue that this system is not a binary system, but also can be as a chirping ellipse. Well, in this table, I show you the equivalence between the parameters of a cell and a binary for some binaries. For example, for a cell and a binary detected at 9.20 millihertz, the chirp mass is 0.32 solar masses, and the mass of the cell is 1 solar mass. Also, well, you can see here how the two systems, the two templates, dephase over 1 year of observation, and the dephasing is really small. Also, these systems are not only degenerate with double white dwarfs binaries, yes, binaries that are composed by two white dwarfs, but also with a system composed of a black hole and another type of object, like in a string mass radio inspired. Yes, so we have two types of binaries, one composed by a string mass radio inspired, and one that is a double white dwarf. And the next question, the next obvious question is, what are the rates of formation of these objects? Yes, because one thing is that mathematically we have found that the two systems are degenerate, but what the question is that if these systems are naturally found in the universe. So we have calculated from the binary white dwarf mergers that can give rise to these chirping ellipsoids of the post-merger object, and the rate is given by the maximum rate of 0.45 per year, and it's comparable to the rates of Embry, and also to the compare of the merger of double white dwarf. So the rates of all these systems are comparable, so we can say that they are degenerate. So as general remarks, I show you that the cells are quasi-monochromatic, these ellipsoids, and are detectable by planned space-based interferometers. And the cells are degenerated with two kinds of binaries, the Embry's and the double white dwarfs. And well, this is the first degeneracy, but this is related with the detectability of Embry's. But I'm going to focus on the degeneracy between cells and double white dwarfs. And we can also, and I also show you a partial solution to break degeneracy, that is the chirp of the end of the chirping phase in the systems are different. So we can distinguish between the two systems if we see if we can see the end of the chirping signal, because the double white dwarf ends before the cell. So if we see a chirping signal with a very high frequency, we can argue that this is more likely to correspond to a cell. So thank you. Questions?
Jose?
Hello?
Jose? Yes, it's
Yes,
Jorge.
yes, Jose.
Yes. So, my question is, so these cells, the cells are, so you think the cells are mainly produced in the first stages of the post-merger evolution of double white dwarfs?
Of the cells? Oh, the cells are the post-merger object of a double white dwarf merger, double white dwarf mergers, the post-merger object. And well, I make a distinction between the cells. These are the aftermath of a double white dwarf merger, and this the first one I presented that are the aftermath of the core collapse of the carbon oxygen core star in the binary driven hypernova scenario. So these two objects are different. The first one is a neutron star and the second one is a white dwarf. But as you can see, you can, and this method can be used to analyze many physical scenarios. The first one is the binary driven hypernova scenarios. Also, you can analyze pulsars, the Crab Nebula. Also, you can use it to analyze the post-merger object in a binary neutron star or in a double white dwarf.
Do you expect big differences in a general relativistic framework?
The general relativist framework. Oh yes, but first, this we assume that this is Newtonian. The objects has let's say they are rotating slow. So in the general relativistic scenario, we are going to compare. But I didn't work the scenario in a binary neutron star that relativistic effects are more important. But regarding double neutron stars, we are comparing now with simulations, full simulations, 3D simulations of double white dwarf mergers.
Okay, so thank you. Any questions from the additional questions from the audience? No more questions.
Okay, thank you.
Thank you very much, Jose. Okay, thank you. Therefore, we are going to stop at this point with the session, and we see you everyone tomorrow, 9 o'clock, and the updated program is in the web. You can see it. Thank you very much for participation. Have a nice day.